Okay, the first speaker today is Romain Tessera.
This afternoon.
What?
This afternoon.
What did I say?
Today.
Okay, didn't say this morning. He's going to speak on coarse separation in hyperbolic groups.
Thank you very much for the invitation. I'm really glad to be here. It's my third time I think in Cambridge, and I really enjoy it. Yes, I'm going to talk about a notion of coarse separation in metric spaces, which, sorry, this is your, my mess is here. So I'm going to start with, I don't really like to do that in general, but here I think it's important somehow to give you a definition to start with, because everything on my talk is going to essentially discuss this definition and exploit it. So I'm going to start with the definition, which is actually not the technical one, because I mean, the notion is supposed to be a coarse notion. So when we want to define a coarse notion, generally you want to make sure that it's invariant of the coarse equivalence. So you define it for general metric spaces, and you put constants everywhere, and it's messy. So I'm going to cheat a little bit and give you a definition which is going to be almost good enough for the talk. Maybe at some point, if you are careful enough, you will tell me, maybe here, your definition is not quite exactly the one you should need. And I'm really happy to have such a reaction, so don't hesitate to be a little bit picky and tell me at some point, well, your definition here should not work. Okay, so here is the definition I'm going to give you. So first of all, it's not going to be for a general metric space, but only for a graph. So let's say that X is a bounded degree graph. Bounded degree is not that important here, but it's going to, I mean, we are going to apply it in a situation, I mean, only for Cayley graphs or this kind of thing, so it doesn't really matter. Graph. And let S be a collection of subgraphs, subsets. So we say that X is coarsely, strange sound here, separated by my family S if for every R big, I can find there exists S, one subspace in my family, such that if I remove S from X, meaning that I remove all the vertices, all the edges, whatever, it doesn't really matter. If I remove X from X, then I can find 2 points, X and Y, in X minus S, which are in different components, in different connected components. Such that, so far I'm just saying that S separates X in 2 different components, which are non-empty. But now I need to justify at least a little bit why I have coarseness somewhere. So this is where some coarseness is showing up here, the minimal amount, such that X and Y are sufficiently far from S. Okay, so such that the distance and the distance from X and Y from S is bigger than R. So let me give you a bunch of examples. For instance, let me draw a picture maybe. So it means that, okay, I have my space X, I have S here, and what I want to have 2 points, X here, with a distance bigger than R, and another one on the other, in a different connected component, Y, which also is at distance at least R, okay? So, let me give you an example. For instance, if I take the half line, okay, the half Cayley graph of, or the Cayley graph of N, this guy, so here it's infinite, this guy is coarsely separated by the set of singletons. Why? Because if I take only one such singleton, then this singleton, of course, will not separate my set into two infinite components. One of them is going to be finite. But if I can, given some R large enough, I can go sufficiently far away to make sure that at least I have two components of size R. Okay. So of course it's better if I have just Z, then it's also true, and I need only one point. I need only one singleton. Then it's constantly separated by only one of them, not the whole collection. Okay, so let me focus a little bit on the situation where the family that constantly separates the point are bounded. So first of all, let me just define diameter of the family. So suppose I have a family of spaces. Here, family. Let me define the diameter of a family as being just the supremum of the diameter of S. And in the same way, we are going to define the volume growth and so on, but we are going to do this a little bit later. So, and now suppose that, and let's say that S is bounded if its diameter is finite. Well then, let me give you a definition. We say that X is uniformly one-ended if it is not coarsely separated by a bounded family. So let me give you an example. For instance, if you take any tree, any infinite tree, is not uniformly one-ended, although it is generally one-ended. It may be one-ended, like for instance this example over there is one-ended, but it's not uniformly one-ended. So uniformly one-ended implies one-ended, but not the other way around because of this example. But if the space, if X is vertex transitive, then the two are equivalent. Okay, and the reason is roughly that in order to have one-ended, you need to have two infinite components, and here you will vary the finite sets to have bigger and bigger connected components, and by a compactness argument, you will, because the graph is vertex transitive, you can move things around and still keep the same. You can use compactness argument to prove that. So it's not very hard. So, but the good thing about this way of defining separation is that it gives you a notion that is kind of more workable when you are not working with necessarily vertex transitive graphs. In certain situations, it is interesting, although I'm not going to define it here. Yeah, the question is, can we define, well, before the question, sorry, I'm going to give you a few motivations for this notion. So the two motivations are coming from first graph of groups. And coarse embedding. So the motivation is about the, so I'm going just to simplify to discuss the case where G, I'm taking groups G, H, K, finitely generated group. And I'm wondering when can I have a coarse embedding of G in a free product with amalgamation over a finite group. So L is finite. And I mean, it's well known that if G is one-ended, then G ends up like f of G lies at bounded, in a neighborhood, in a bounded neighborhood of a coset of H or K. And you can easily guess that if you have a more complicated graph of groups, some over finite edge groups, then you get the same type of result, and that's easy. By the way, let me just define what's a coarse embedding, because this is going to be important for this talk. So suppose you have F, a map between two graphs of metric spaces. So let's say graphs. So is a coarse embedding it's a coarse embedding if it is Lipschitz and you need also some control on the other direction, but you don't need a bi-Lipschitz control. So your coarse embedding is a weakening of quasi-isometric embedding. And there exists just a function rho from R plus to R plus, increasing so that the limit tends to infinity. Such that for every x and y, such that you have the following inequality: rho of dxy is less or dxx prime, sorry, in x is less or equal than the distance in y of f of x. Do I do it in the way? F of y. So the Lipschitz condition gives you a linear term here, and here the point is that you can have logarithmic. You can, for instance, you have if you have a distorted subgroup, finitely generated subgroup, then the embedding is a coarse embedding. It's never, generally, it's not going to be a quasi-isometric embedding. So yeah, one of the reasons why we introduced this notion of coarse separation is because we wanted also to have, we were trying to have tools to prevent coarse embeddings between certain parallel spaces, and or at least to constrain the coarse embeddings to get some information. So here is one motivation, and actually the original motivation was not this one. It was coming from our study with Anthony Genevois. So the second motivation, the original one, so it was coming from the study of Riesz products of groups. So let me remind you what the Riesz product is. So you take A, B to be groups, and the Riesz products of A with B is just the direct sum of copies of A's indexed by elements of B, semi-direct product B, where B acts by permutation of the copies. What's good about this notion is that you can make it purely metric. Even if you start with two metric spaces, let's say pointed metric spaces, you can define a Riesz product like that. So it's kind of, it's like a little bit like the free product. The free product, you can also define the notion of free products between families of, between two pointed metric spaces. So that somehow these two constructions can be made purely metric, and all the statements I'm going to say actually can be made to work in this purely metric setting thanks to these uniform notions. So, and the theorem that we proved with Anthony the original one was that if you take G to be finitely presented, and here finitely presented is absolutely necessary, and it's not, you don't have this condition here, it's finitely generated, but here finitely presented plus one-ended. Or if you want a metric space, then you have to assume that it is uniformly one-ended. And if you have a coarse embedding F into a risk product where L is finite and H is finitely generated, then the conclusion is that F of G lies in a bounded neighborhood of a coset of H. And that was really the prelude and the main part of our proof for getting some classification of the Lamplighters for finite groups, finite long groups. It was really the main place where we have to really work seriously, and where we use cat-zero cubical complex and this kind of stuff. But anyway, the thing is that that was a motivation, because then, of course, after we understood quite well what happens when the lumps are finite, we wanted to understand what happens when the lumps are not finite. And actually, in both situations, both motivations, the question that's going to motivate the rest of my talk is, can we extend these results, remarks and results, I would say, but these results, these facts, when we, how can we extend them actually? When L, the groups L, so here, of course, I mean, yeah, I didn't tell you, but the fact that L is finite is directly connected to the one-ended condition. Because finite, bounded, blah, blah, you are in the situation where you're discussing about separation by finite things. And same for there, the fact that L was finite was the reason why one-ended was the right condition. So where L is infinite, but say small. So, well, when you work with Lamplighter groups, the first case you want to understand is replacing a lamp, which is a finite group, by Z. Z is polynomially growing. Actually, it's not Z that will show up really in this kind of statement. It's going to be a direct sum of copies of Z, a finite direct sum of copies of Z, so it's going directly to be an infinite, I mean, to have polynomial growth with a potential large degree. But somehow, let's discuss, for this talk, I'm going to give a precise meaning of small, and I'm going to require that H has sub-exponential growth.
Sorry, Romain, maybe I missed this explanation. Where do you mean finitely presented with this theorem?
It's a little bit tricky. It's because you don't work exactly with the map to the risk product. What happens with the risk product is that, in order to understand the fact that it behaves like some kind of tree of spaces, the Lamplighter doesn't, but if you cut the presentation of the Lamplighter, you get a finitely presented thing, which looks a bit more like a tree of spaces. So having that G is finitely presented, you can lift this map, this coarse embedding, to a coarse embedding into a finitely presented group obtained from this by cutting the presentation, which is always infinite. And then it's more complicated even than that, but you can play with the map below and the map above to show that you have some relative tree-like behavior of this guy with respect to the cosets of H. But it's a bit complicated. I mean, this talk is not about this. And actually, another thing which gives you why this statement is completely false if you don't assume that G is finitely presented is you can take G to be equal to this guy. And definitely, the group itself is not lying at the bounded neighborhood of H. So it's really important. I mean, this condition is absolutely necessary for this statement.
So you're using some sort of Rich-type theorem in the end, or not?
If you don't mind, I can explain to you, but it would take really a lot of time because it's not an easy result. So in order to proceed, I'm going to define.
Sorry?
Yes.
This H is L, is it H or L? That has some H.
So f of G lies in the bounded neighborhood of H. So really this.
No, there.
Smaller line.
It's
Oh yeah, sorry. Thank you very much. L. Thank you. Thank you. So yeah, I need to introduce the notion of volume growth of S, my family. So let's say that Vs of R is going to be, so remember that S is a family of subspaces, so this is important actually, is going to be the supremum over X, over S in S, and X in S, of the size of the ball of radius X and R in X intersected with X. So let me comment on this definition. So first of all, the idea is that we take the maximum size of balls of radius R over all elements, not only centered over all possible points in S, but also over all elements in my family. So I take the maximum degree, the maximum growth of whatever ball you can find in one of these families. But then another important thing is that this thing here is the ball of radius R in S for the induced distance. So it's not an intrinsic distance. S is a subset. It doesn't have to be connected at first. You know, it's like it doesn't have a natural graph structure. It's just a subset, subgraph if you want, but it could be non-connected. And so I'm measuring the growth with respect to the ambient space. And that's quite important because it's not going to be the same if there is distortion. I'm going to take the distortion into account. Okay? So that's the volume growth of S. And now let's define a class. So I want a good notion of not being separable or coarsely separable by a sub-exponential growth subsets. Okay, so here, this is just take it as a general goal. Now I'm going to give you a good definition. Okay, so that's what this definition is supposed to do. So I say that X belongs to the class MX if every coarsely every family S that coarsely separates X has exponential growth. So it's a very strong statement. It says that in really like it's very difficult to cut your space. I mean, if you cut your space, if you separate your space, then you have to have exponential growth. That's what it means. So you cannot be separated by let's say sub-exponential growth, subspace alone, or not even a collection of these. Okay. So that's my definition. And the first thing to say about it is that, let me first tell you, explain to you how why the motivation is fulfilled by this definition is that the applications are that if you take, so the two statements about graphs of groups, or free product, let's say, with amalgamation of groups and with products, are satisfied with the same proof, basically, if we assume that L has sub-exponential growth, and that G belongs to MX. Okay? So you replace 100 by MX, you replace being finite for L by sub-exponential growth, and you get the same results, okay, with the same proofs. One of them is, you can guess what it is, the one for the free product with amalgamation. Somehow it's a tree of things, and it's easy to see. For the other one, it's more complicated. I'm sorry, I cannot explain, but at least the same proof, the same arguments give you this. So now the whole question now is, we want to understand which group belongs to this class. Okay? So the rest of my talk is going to be.
What do you mean, the group? So it depends on paragraph?
No, well, I didn't say that because also my definition was not that coarse, maybe, though I think it's probably sufficiently coarse. But the fact that you belong to MX or not is invariant on the quasi-symmetry. Maybe I should say that. So a few remarks. So the remaining of my talk is going to be about study of groups with study of the class MX. I mean, the ones which are inside and the ones which are not inside. And in particular, hyperbolic groups, but not only hyperbolic groups. So the first remark is that it's stable on the quasi-symmetry. Okay, so it's really a geometric property. And then there is a theorem with Ben Said, which under this generality, it was not so easy actually to prove. We only proved it recently. I mean, the whole project started a year ago, so it's quite recent. And it's even in progress somehow. But this full result took us some effort, so it is stable. So if X belongs to MX, and Y is any graph, then X times Y belongs to MX. But it's not so easy, somehow. It's not completely obvious. It's not extremely hard either, but it's not completely obvious. Although it seems kind of intuitively straightforward. It's good. Now, what can we say? A few examples and counterexamples. So BGT stands for the three of us. Like if you take, so let T be the 3 regular tree, or K regular tree, it doesn't really matter. The 3 is not so important here. Then you have that T times T belongs to MX. A smaller space, a subspace of this is the Lamplighter group. For those who know, the Lamplighter is a horocyclic product of two trees. It is also there. So Z mod 2 times Z belongs to MX. So really, this one is almost surprising because it's very thin, but not sufficiently. Like, it's still difficult to cut it. And for instance, for symmetric spaces and Euclidean buildings, are all in MX, except for the trivial ones, which for the trivial exceptions. So what are the obvious exceptions? I should say, well, this is not exactly true. Symmetric spaces, Euclidean buildings without Euclidean factor. Or I could put it in, okay. I'm just putting them in the trivial exceptions. So the trivial exceptions are, for instance, H2. Why H2 is an exception? Because H2 you can cut it with a geodesic. Geodesic has linear growth. So surface groups are exceptions. Okay. But as soon as you look at H, and of course if you do H2 times Rn, it's also going to be an exception. So if you have Euclidean factors, then it does not really affect anything. So, but if you take H3, it's already, yeah, it's not so, I mean, it's not obvious. You may think that if you, obviously if you take, if you want to separate it with the totally geodesic thing, then it's kind of clear it's not going to work. It's going to have exponential growth because it's going to be a copy of H2 of R, which has exponential growth. You might think that maybe I can take a horosphere, because the horosphere has polynomial growth, but it has polynomial growth only for its intrinsic distance. But here we are interested in the induced distance, so the horosphere actually has exponential growth. So this one actually belongs to MX. And it follows from the theorem. Now, more recently, we managed to prove something that went a bit further than that somehow. So, BGT 25. We managed to, I have something I should tell you first, maybe. Oh, I'm going to tell you after I state the theorem, doesn't matter. So if G is hyperbolic.
Sorry,
Yeah.
did you complete the list? I guess trees should be part of the exception.
Yeah, trees. Oh, yeah, thanks. T exceptions. T times R exceptions. Thanks. So if G is hyperbolic, then G belongs to MX, belongs to MX, if and only if G does not virtually split splits over 200 groups. So when the group splits over 200 groups, then you know that these groups are never distorted, so it gives you automatically it gives you a linear separation. Okay, so that's definitely, I mean, this condition, I mean, the fact that Q splits over a 200 group gives you definitely an obstruction for belonging to MX. Okay, but the theorem says that as soon as you are not separated by a quasi-line, then you are actually not separated by anything of sub-exponential growth. Okay? And actually the proof uses some lemma in a recent paper by I don't want to forget or to misspell one of the authors. So they are in this room, some of them. Happy to. No. It is somewhere. Sorry. Oh my God. Okay, I'm going to try to remember. So Lazarowicz. So maybe I will ask for help. Lazarowicz. There is a guy I forget, and Mahan, MG. What? Margolis. Yes, of course. Thanks. Actually, a similar lemma appears also in the PhD thesis of John Mackay. So it's, never mind, it's about things happening on the boundary of hyperbolic groups which do not split over 200 things. So we still have some work to do. It's not just a straightforward consequence of this lemma. But what I mean to say here is that there are techniques that were already there somehow that could be used for solving this question. And so a nice consequence of that, a corollary, is should remind you a little bit of a theorem of Papazoglou. It says that it's a coarse embedding version of, not exactly as strong, but of Papazoglou's result, is that if G is finitely generated, if G and G prime are hyperbolic groups, and if you have F, a coarse embedding from G to G prime, then it maps vertex groups of the GHG decomposition to vertex groups. So in Papazoglou's result, you start with a quasi-symmetry between the groups, but the result is stronger because it's not only about vertex groups. It really says that it respects somehow the graph structure. And here we don't really know if the adjacency between the edges, the vertex groups is preserved by this coarse embedding. So there is still something to be understood to have a result as strong as the one of Panos. Okay. And next I'm going to write down the last theorem I want to state, and with the time I will tell you some things about the proofs and techniques and stuff like that, and also open problems. There are a lot of open problems. So for RAAGs. So for RAAGs, we can also get a complete answer. So the theorem we get with Anthony and Usama is that so gamma is a finite graph, and write A of gamma the corresponding RAAG. So you know what a RAAG is when you have a finite. Okay. A belongs to MX if and only if the obstruction, the natural obstruction that you might guess is not satisfied. Namely, there is no separating complete graph in gamma. Okay. So So in other words, you don't want to be like that, for instance. So this is a counterexample. This is not allowed, obviously, because so one direction is obvious. So if you have a complete separating subgraph, it means that you have here Z3, which coarsely separates. Why? It's because your group is actually just an amalgamated product over the Z3, okay? And moreover, the Z3, we know that in RAAGs, these abelian subgroups are not distorted. And that's also important for this result. You don't want them to be distorted. So here it also gives you something that's a little bit unexpected, maybe not unexpected, I don't know, but the fact that it's not only when you are not obviously separated by, coarsely separated by an abelian subgroup, you cannot actually be coarsely separated by anything which has sub-exponential growth. Not even a subset. So, okay. So now that I've stated all the results I wanted to state, let me maybe tell you a few open questions which we really don't know at this point. It might well be that that a similar statement holds for Coxeter groups, right-angle Coxeter groups. We don't know what happens there. We don't know the full answer for right-angled Coxeter groups, which are more general, as you know, because, and more generally, I mean, it would not be completely impossible to, although this is maybe a long shot, I don't know, but I mean, maybe a similar result formulated correctly could work for any co-compact tubulated groups. Okay? So, more generally, of course, it is more difficult than these questions. So, K0 cubical complex groups. We don't know, I mean, and of course, I mean, we don't know for many things. I mean, but, yeah. But these specific classes, I mean, there are chances that some of the ideas we had to treat the class of right-angle arcing groups could maybe apply. The thing is that at some point there is a lot of reduction to certain cases that we understand well. So also we don't really understand what's happening for relatively hyperbolic groups. Now we understand perfectly what happens for hyperbolic groups, but for relatively hyperbolic groups, we don't know. We don't really know. I mean, maybe some of the techniques also should extend, but it's, well, we haven't thought maybe sufficiently hard about it, but we don't know yet. And actually, dealing with the relatively hyperbolic groups case would help us a lot for Coxeter groups, because they're. Okay, so now, how much time do I have exactly? Like 6 minutes. So yeah, that's good. So, well, if you have any question, of course, don't hesitate to ask questions. But I'm going to explain to you a little bit. I mean, some of the techniques we use. So, I mean, one of the main tools in this story is the notion of cut that is very old. Cut of finite graphs. So the notion of cut of finite graph is like the finite version of what I've discussed so far. So you take a finite graph, so let gamma be a finite graph, and define the cut of gamma to be the minimal size of what? Of, let's say, S separator in gamma, such that gamma minus S has connected components of cardinality at most the size of gamma divided by 2. The fact that we take the size of gamma divided by 2 is a little bit artificial. You could replace it by the size of gamma divided by 3/2, or multiplied by a number which is less than 1. It doesn't really matter. I mean, for the definition, it matters. It does not give you equivalent definitions. But when you start looking at bigger and bigger subgraphs of a given graph, then it does not really matter. So using this notion of cut, you can define the separation profile that has been introduced, defined by Benjamini, Schramm, and Timar. But this is not what we are going to use here. So we have studied this quite a lot with John Mackay and David Hume. But here it's a different direction where we are going to focus on the cut of balls. Okay? And so the main tool for the proofs or the previous theorems is the notion of cut of balls. cut of balls that we're going to write as I don't know, theta x of r. Okay? So it's a function which does not necessarily have to grow. I mean, to be monotonous. We don't really care. What's important for us is when we want to show that a space belongs to Mexp, what we need to prove is that this cut is large. Roughly speaking, the idea is that we want to prove that this cut grows exponentially, that this quantity grows exponentially. So, to prove that x belongs to Mx, it's enough to show that theta x of r grows exponentially. It cannot grow faster than exponentially anyway, because we are in a bounded degree graph, and so this quantity cannot be bigger than the size of the ball itself, which is exponential. So we need to show that the balls are difficult to cut. So why is it enough? Well, the idea for the fact that it's enough is that balls, there is a reason why balls are good. You could replace balls by different kind of sets, but the important thing is that you want to be able to slide balls. And you want the sliding to be continuous in some way. So you want that when you take a ball of radius r and set it on x, if you slide it along a path, so you take x prime to be just a neighbor, you want the two balls here, same radius, to have a large intersection, an exponential intersection. So what you want, the condition that's really important here is that you want the intersection of these two balls you want it to be exponentially large. And it's always going to hold for balls, because if you are in a space of exponential growth, which clearly we are considering, the intersection of these two balls contain the ball of radius of center x and a radius r minus 1. So it's going to have exponential growth. Okay. And actually, what you need a little bit more than that, I should say. I'm not being precise here. So what you actually need, is you need this to be proportional, You need to be bigger than a certain proportion of the ball of radius x. You want to miss at most a proportion of the ball of radius x. And the reason is that the idea of the proof is going to be that you take a separation, you take a separator, which is such that x and y are at distance r from S. So that allows you to find a ball of radius r which is completely contained in one of the components, and another one which is completely contained in the other components. And now you're taking a path between x and y, and you're sliding your ball until it hits the separator. And at some point, because of this continuity condition, the ball along the path is going to be cut by its intersection with S. And if S has sub-exponential growth, then this is going to violate the fact that this thing is exponential. So the idea is relatively simple. And basically, most of the proofs consist of extending this idea, because so this is the first step somehow to prove, for instance, the hyperbolic case or many situations. But when you have more complicated spaces, you will start with a space which has this coarse separation, and you will slide the space itself. So you will replace this argument with the ball with a subspace that you're going to slide, or these kind of things. For instance, in a building, you can use the fact that you have a lot of sub-buildings which intersect a lot, and you can also use this kind of sliding argument. Okay, so that's the main general idea for dealing with these results. But for RAAGs, you had to be a little bit more inventive, because basically the idea for the key idea for RAAGs that allowed us to get this result is that first of all, there is a reduction for RAAGs. There is a reduction to the case where we don't have squares. It's a technical reduction which uses these kind of arguments again, but in a bit tricky way. But once you don't have squares, why are we happy? Why is a RAAG without square better than other RAAGs? It's because when you look at the corresponding Coxeter group, it's hyperbolic. It's hyperbolic, and if it doesn't have separating complete subgraphs, as we assume as well, it's hyperbolic, and it's not, it applies to, I mean, it fits in this theorem. So it's not separable by a sub-exponential growth thing. So now I have my RAAG, and it projects down to a Coxeter group, which satisfies this condition. Now, how can I, somehow, what do I want to do? So the idea is that, and that's a statement that I'd like to write down because it's kind of fun. Oh, no, I'm too small. I'm going to write it down here. So it's a theorem which says that if A of gamma, assume that gamma is a Morse geodesic in A of gamma. So A of gamma is my, I'm not making any assumption here. I'm just taking any graph. Okay. We are going to apply it in the situation I described earlier, but the result is completely general. So suppose you have a Morse geodesic in A of gamma, and let's say that X belongs to this Morse geodesic. Then there exists a quasi-asymmetrically embedded copy of the corresponding Coxeter group with a sufficiently large parameter. So M being the size of the, so it's Z mod MZ that you have on each group, on each vertex group. So M is large. In A of gamma, passing through containing gamma. Actually, we don't need that. Containing gamma. And that's how we, so basically the proof then consists of showing that if you have square free, which is the assumption we can work with directly, then actually the group is asymmetrically hyperbolic. So you can find a Morse geodesic somewhere. And this Morse geodesic, then you will construct a copy of the associated Coxeter group going through it. And actually, what you can prove is that not only you have a Morse geodesic, but you have a full tree of Morse geodesics, a full Morse tree going through every point. And that's enough to show that if you have a separator, which is sub-exponential growth, at least one of these, in this tree, which is a binary tree, you will have at least one Morse geodesic that's going to end up in different components. So you know that this Morse geodesic is going to be separated by your S. The next step is to show that the Morse geodesic itself is not that interesting, but if you can show that S is going to cut a copy of these Coxeter groups, which cannot be cut, then that's going to give you the contradiction. So that's the way we proceed. So first we find a Morse geodesic that's separated by S. Then we lift this Coxeter group quasi-symmetrically along this Morse geodesic so that it becomes cut by S, coarsely separated by S, and that implies that it cannot happen, the assumption. Okay, so I think I'm done. Thank you for your attention.
Any questions?
Yeah, do you think about right-angled buildings? any examples of where they've been Coxeter groups?
So Euclidean buildings we know. We know also the Bourdon-Pajot buildings because they are hyperbolic, so they fall into this class. But other than that, we don't know. For the non-hyperbolic buildings, with hyperbolic chambers, we don't know. We haven't thought about it. Well, thank you.
Any more questions?
Yeah.
So this board over here has a result about Reith products, and the motivation included as a special case a conclusion about free products. In between those is the result for graph Reith products.
What is it?
You just declare some pairs of orbits as H, not all of them.
I don't know. We have a wider class of groups which generalize Reith products, which we call halo products, which encode which for instance include the case where instead of the long group you have the finitely supported permutation of H, these kind of things. But for the ones, the graph, I'm not sure it satisfies our conditions. I would have to think about it. We have some conditions that have to be satisfied for. It cannot be, the graph has to be right. You don't want to have too much correlation, because then you could even have a finitely presented group, and then it would definitely, all the machinery would completely collapse. So it cannot, to some extent, it cannot cover too general stuff. But maybe we can discuss later. So you didn't tell me where I was imprecise. Doesn't matter. Well, thank you.
Okay. So, thank you.